Well, it's a pleasure to be here. I have a whole bunch of stuff to show you, so I'm going to jump right in. As you heard from the introduction, I teach astronomy, and a lot of it's based around these telescopes that we've built in the Chilean Andes. So I think I'm going to be hopping back and forth between lots of things, and a little pixel limited here, but I'm going to start by showing you the observatory. It's Cerro Tololo Inter-American Observatory. It's one of the best places to observe on Earth. I'm going to show you the telescopes. I'm going to describe just briefly the science that's been done with these scopes, and then move on to the education and public outreach that's been done in parallel. But while we have the connection to Chile working, I'm going to take advantage of that. It's sometimes flaky. So here are the telescopes. It's called PROMPT, which is an acronym, a very contrived acronym, so I won't bother you with that. But we have 6 small telescopes. And by small, I mean 16-inch diameter, so the mirrors are about this big. And we're in the process of building a 32-inch diameter telescope, so the mirror's about this big. And there'll be another telescope kind of back here that's a 24-inch. These telescopes observe invisible light, the same wavelengths that the human eye operates at. The big one here in the front will observe in the near infrared, so redder than the human eye can see. The other one's going to be a specialized instrument that does polarization, the orientation of the waves of light. Let me just back out and show you the terrain a little bit. Now I should say these are robotic telescopes. They're not just any telescope, but they're robotic telescopes, which means no humans are necessary at the scope. We do go down a couple times a year for maintenance, that kind of thing, but most things that go wrong we can fix remotely. These telescopes belong to someone else, but let me just kind of zoom around the observatory. You can see it's very dry. This is about an hour-and-a-half drive from the Pacific Ocean up into the foothills of the Chilean Andes. This is the cafeteria. Last time I was there for breakfast, we noticed there's a tarantula crawling on the floor. You check your bed for scorpions before you go to sleep. It's that kind of place. Come on. There we go, moving around a little bit farther. Residence hall. The internet's a little bit slow today. If I go over 2 more clicks, there's another set of telescopes I want to just briefly mention on this mountain over here. So it's a 2-mountain observatory, and on the other mountain we have currently 2 telescopes. The one on the left is SOAR, UNC effort. The primary mirror is 4 meters, so a pretty big telescope. The one on the right is Gemini South. Its mirror is 8 meters. It's one of the largest telescopes on Earth, and we have regular access to this and sometimes access to this. But let me go back to our PROMPT telescopes. These are different than the big telescopes because the big telescopes are still human-controlled. This is a Q-scheduled system with small telescopes. These telescopes, since we started building them in 2004, they've taken 4 million exposures for 30,000 different users. Most of the exposures are science exposures for hundreds of scientists across the state and the country and the world. But most of the users are students, elementary school all the way through grad school. The elementary school students use a different interface that's kind of simpler to use, and the middle school students. The high school students, the undergrads, the grads, they use the same interface as the professionals, and something that's still being improved upon daily. Now let's see, I want to show you one of these telescopes up close. I'm going to show you PROMPT 4, and I have another webcam here on the inside, and I have audio going. I thought well, that's okay. You can hear it through my microphone here. You can maybe hear that. So what I have on this screen over here is a team viewer session. So this is the desktop that's in that particular building. And currently we have a bit of a delay with the video service here. This is commercial video service. But what I'll do is I'll do a few things. The last time I checked it was about a 15-second delay. I'll turn the lights on. There they go. And I'll move the scope around. Now this is not the usual way of using the telescope. This will go in about probably 5 seconds, and you should be able to hear it. There's my speaker. 4,000, 5,000 miles away. All I had to do was click a few buttons. So it's pretty easy to use, but you can't have everyone logging into a single computer, particularly if you have 30,000 users. So we have a web page, and we queue schedule through them. So most people don't go on the way that I'm using it right now. Now, I'll do one other thing. Let me turn the lights off because I always forget, and then that ruins the images at night. I have a team of about 12 students, and postdocs and programmers, and they're all going to log in when I'm done with this because they know I tend to leave things in a hectic state here. So I'm going to open the dome, and there's no video lag on the external webcam, a little bit of one on the internal webcam. Now, of course, check the weather before I did this. Being robotic telescopes, we have weather station. If it gets too humid or too windy, it will shut down. If it starts to rain, it should be closed already. So it's just a quick introduction to the toy that we have to play with. And what I'm going to do is just show you how smart Skynet is. Skynet's the name of the system. Let me close this down. That's the dome control. And yeah, so you're thinking Skynet. That sounds familiar. There's one copy of Skynet, and we wrote Skynet, and it lives at Chapel Hill, and it controls a program called a Terminator at each telescope. So here's the Terminator. And the Terminator is done by design. It does what it's told, and it controls all the various components of the telescope, which I was just playing around by, or playing with by operating these other programs the Terminator usually controls. I'm going to just turn Skynet back on. It would take a second. And the Terminator will report to Skynet saying, hey, it's the middle of the day, the dome's open, the telescope's in the wrong position. Sounds like Dan was doing a demo, and it will clean everything up. At least it should. It takes about 10 seconds, but... You don't have to worry about creatures getting in there, into the spiders. You don't have to worry about things crawling in there? Yeah. Different things. I don't know why it didn't close up, actually. There it goes. Good. Yeah, different things get in there. Bugs, spiders, nothing big. The door's pretty tight, and it's pretty high up to jump in at night. We once had a bug in our image. We got an image back, and you can see the bug. It was standing on the camera opening. That's a literal bug in the system here. Okay, so those telescopes are called prompt, as I said. They're controlled by Skynet, and here's one up close with me next to it to make it look cool. And I'll just show you one little video here. Not sure where it's going to come up. Came up over here. And this is what happens every evening when the sun is 1 degree below the horizon, the dome's open, and then the telescopes will slew in position, get ready for the evening's observations. And they're all very busy every night. You can see them all moving in unison. Okay. But I've spent more time on that than I wanted to, so I'll come back here. Okay, back to the power. Oh, yeah. So the control system. I said we can't have everyone logging into the same computer, so it's done through a website. So here's the website here, Skynet. And right now, you can only have access if you put a telescope on the system. What I've showed you so far are the telescopes we've built, but the system has been so productive that other people have come to us with telescopes of their own that kind of meet the standards that our telescopes have, and so we've put them on the system. We have telescopes across the U.S. that don't belong to UNC, and anyone who puts a scope on the system has access. There are other ways to gain access. We're always looking for ways to expand it as well. But I'll just show you how simple it is once you do have access. And so you just add an observation, and you don't need to know the coordinates. Let's look at the Tarantula Nebula, a good southern hemisphere target. And it looks it up, fills in everything you need. I'm going to lower I have top priority. This isn't critical, so I'm going to lower the priority. You pick what color light you want to look through. I just picked no filter. And it searches all the telescopes in the world that can observe this target, and you select whichever ones are acceptable to you. The first one available will do it. Suppose I want one 80-second exposure. It goes in the system, I confirm, and now it's scheduled. Of course, it's daytime, so it won't go right now, but tonight when the telescope's open, it'll take care of it. This is one I put in a few days ago, and just a little preview of what 80 seconds on a small telescope gives you, a little snapshot of the Tarantula Nebula. So pretty easy to use. Let's go back to the PowerPoint here. If I know how to. Okay, so let me talk a little bit about the science, then I'll get into the education, which is what you're all really interested in. We built these originally to chase cosmic explosions called gamma ray bursts. They're massive stars that reach the end of their lives, collapse, and form black holes. So we actually watch black holes being born, or seconds afterwards. They produce a lot of gamma rays that don't make it through the atmosphere, but NASA has spacecraft up there which monitors the sky in gamma rays and sends coordinates down to our cell phones, can go off at any time. About once every 3 days we get one. It also goes directly to Skynet, which takes charge of all the telescopes on the network. And the primary ones are the prompt telescopes. Here's just an example of what it sees. This is actually the most luminous thing ever seen. It was bright enough to see with the naked eye, but it was about 3/4 of the way across the observable universe. And these are just seconds and minutes later. You can see how quickly they fade away. And that's why we built robotic telescopes. There's not enough time for a human to run to a telescope and pull off these observations. This is about 20 minutes later. And the biggest, we've observed many of these gamma ray bursts. The biggest, most exciting one happened a few years ago where we observed with multiple telescopes. With the SOAR telescope, we found a fading afterglow in the infrared. But with the prompt telescopes, we saw nothing in the visible. And this is the signature of something really, really far away. Astronomers call it dropout. If you can see it in the infrared and there's nothing there in the visible, you might have just discovered the most distant thing in the universe. And this particular object exploded 12.8 billion years ago. And the universe is only 13.7, so we made it back into the first 6% of time. I mean, this was before the sun, Earth was even here. And it was the most distant explosion in the universe, and we held the record for 3 years. So you could do some impressive science even with these small telescopes. I'd like to point out the first author we published in Nature, it was an undergrad who carried out the observations because the system is so easy to use. And so he got to be first author in the Nature paper. Not bad for an undergrad. Now the telescopes are shared, by the prompt telescopes anyway, are shared by these institutions. We have half the time at Chapel Hill. I sell some of it to help pay the bills. And the whole operation, Skynet, costs about $250,000 a year. So I'm always looking for ways to sell out. But there's 20% of the time is reserved for undergraduate institutions across the state. And I didn't know what they were going to do with it, but they've just done amazing things, both on research and education. I should also point out Moorhead Planetarium, which is the biggest planetarium in the southeast of the country, and the U.S. and Chilean astronomical communities. The Chileans, they just kept looking at galaxy after galaxy after galaxy. Let's see, where'd that come up? Here it is. And after like a couple years of this, I asked them what they're doing, and they're looking at supernovae. If you watch this galaxy, you see this little object here. This is a star that explodes and fades away. Prompt, it turns out, I didn't even know it, is the leading discoverer of supernovae in the southern hemisphere. It's also the leading tracker of NEOs, near-Earth asteroids, the ones that could hit us in the southern hemisphere, and in the northern hemisphere with another telescope controlled by Skynet. Some of the asteroid work that they've done has also been published in Nature. But just about every type of variable brightness object, transient object in the sky that you can do with small telescopes, we have exoplanets and everything. And now the various users, I do about one of these publications a year, but we're now up to a rate of publishing about once a month by all the different users of the system. And this, as I said, has led to expansion. We have telescopes across the US, one in Italy, and National Science Foundation just funded us to build a second Southern Hemisphere site in Australia. So it's a rapidly growing system. Oh, and also, I just want to point out, there's one more cool thing going on in the system. It's a giant radio telescope. Just for scale, this is a door. And this will be available not just to professionals, but to the undergrads and high school students as well, to observe in the invisible universe. And you can do all sorts of amazing things. So we're in the process of building a radio version of the system, and the two will go together. But now into education and public outreach. Moorhead Planetarium and Science Center, we teamed up with them. They used their 10%. They created a curriculum for high school students that met North Carolina graduation standards, Earth and Environmental Science, which is where they do astronomy, and trained 75 teachers who continue to this day use this curriculum. Thousands of high school students have used it. They're showing up at UNC now, and I'm giving recruitment talks, and I show them Skynet, and they said, yeah, we used that in high school. So I think that's kind of a good measure of success. Also, we have a simple interface that I won't spend time on right now, but you click on the object you want, type in your email, Skynet will take the picture and email it to you within a day or two. We've had 20,000 visitors to Moorhead Planetarium use this, most of them elementary school students. And so here's our Google Analytics map. We cover users all across the state, rural areas, Our pages have about 64,000 visits per year at this point. But the thing that I want to show in particular, let me check my time here, I'm doing good, is our undergraduate laboratory curriculum. So about 4 years ago, our labs were kind of traditional. Half of the labs were in this very nice planetarium that we have with Moorhead Planetarium, but they're kind of gimmicky, and they suffered from 100% error depending on where you sit. You know, if you're sitting close to the dome, you measure different angles with your hand than if you're far away. The sky is very, very far away, but the dome is much closer. It depends on where you sit. And they didn't really match with the lecture curriculum. And the other half of the labs were done with small telescopes on our observing decks, and we had to fight with Chapel Hill light pollution and weather, and if it rains, there's a weak set of backup labs. Like here's a photo of a fax of a copy of a scan of the moon, measure a crater. Really horrible stuff. And this is pretty standard for introductory astronomy labs. You try to make it work with small telescopes, but most of the time it's fighting with the equipment, which is often outdated anyway. And they built this new observing deck for us that overlooked the athletic field lights. And so students immediately lose dark adaptation, and the building blocked the North Star, so you can't align the telescopes anyway. So at that point, the person who was running the labs for 30 years retired. I became director of labs. I ran them one last time while I wrote this new curriculum that's now fully integrated into WebAssign. And they almost exclusively make use of the prompt telescopes in the Skynet system. So I don't have time to go through it in detail, but the general theme is our place in space, which is a common theme in introductory astronomy. There's a kind of a historical progression where we thought the Earth was at the center of the universe, and we realized, no, it's the sun. But then we realized, no, the sun is actually in the outskirts of this galaxy, and we thought this was the primary galaxy in the universe, but then, no, we realized we're just one of infinitely many galaxies out there. So it's built along this sequence, and astronomically it uses something called the cosmic distance ladder. This is how astronomers measure distance. It's a bag of tricks. Distance is the hardest thing in astronomy to measure. You can't see distance. You see a star, is it really bright and really luminous and far away, or low luminosity nearby? They're a bag of tricks, parallax, standard candles, and so they learn these tricks and measure distances to things farther and farther out and other things along the way. And it's been really successful. We introduced the new curriculum after this year. So in 3 years, our enrollments, not just in the lab course, but in all of our Intro Astro courses, increased by 93% in 3 years. Currently, 1/5 of all UNC students take this, one of our assortment of introductory astronomy courses or more. And this had a nice side effect. With a lot of people going through our introductory courses, with them being fun and exciting, we recruit more majors. Our numbers of majors and minors, BAs, BSs, and minors has increased 300% just in the astronomy tracks in the past 3 years. And it's all kind of leveraged off the Skynet telescopes. And here's another way to look at the popularity. We grab some of their Facebook pages. And this has like great things about the lab everywhere. I'll just point out like one comment that every teacher wants to hear. The most exciting homework anyone will ever do. And, I mean, if you look here, there's high school students saying, oh, I can't wait to go to college and use the telescopes, and it's just great. Here's another one, just pretty damn awesome. And they're posting this stuff on their Facebook page. It's part of the social networking. Okay, so it's not just taking pictures. Let me get to this tool here, Afterglow. We learned this when we pushed the high school curriculum out into the state. They could take the pictures, but then what do you do with them? You need some kind of tool to analyze the images. And they needed something that was free and that they could put onto their high school systems. Most of them are locked down. Most of their computers are variable quality. And they settle on something that's made by the National Institutes of Health and adapted for astronomy. It was clunky and just not very good. So we tackled the problem in building a tool that works not just for students but also professionals. We went into the professional level code. In professionals, they use something called IRAP, which is Unix line command software. It's horrible. It takes like a year for graduate students to learn it. It's miserable to use. We went into that code, grabbed all the routines. So anything that's produced by our software meets the gold standard. You can actually publish it. So it can be used by professionals, but at the same time it's being used by students all the way down to middle school level. And so it's a transitional technology. And you log in with the same password once you have a Skynet account you have an account here. So I'll just log in. And I'll just demonstrate a few things that we do with the labs. And then I'll show you the beautiful product WebAssign put together, wrapped around all these tools. So I'll just do a few analyses. Maybe I'll start by making a movie. Now, this is kind of cutesy. It's not very scientific, but in one of the labs, they monitor one of the gas giants and watch the planets move around them, and they measure the moons move around the planets, measure the distances of the moon, figure out the orbits, and then you can figure out the mass of the planet using Kepler's laws and a little bit of Newton thrown in there. But once they have their images, we do this little thing where they make a movie out of it. And so I'm just going to go through this and show you how easy some of this stuff is. I'm going to grab 15 images of Jupiter. We're loading the headers. Okay, now we're going to load the images. And the thing about this, it feels like I'm doing on my desktop. Those images I just pulled off a server at UNC. All the number crunching is going on at UNC. And they're just sending kind of lower bit images here. The deeper images are there. So it's a kind of a Google Maps interface. I don't have a scroll on my computer. But if you have a scroll wheel, you can scroll, zoom in and out. If you don't, we have these things here. And let me just hit the play button. It'll take a few seconds to get it all into memory, but once it does that, you'll see the 4 famous Galilean satellites going around Jupiter there. That's kind of an oh wow moment for the students. And let me stop it here. It might take a second to stop. And while I was doing that, I'm going to bring up this histogram here and change the scaling. And these images, you can either look at the faint stuff or the bright stuff. Come on. There we go. And so I'll equalize this across the images and play it again. And so there you see Jupiter rotating. So that's another oh wow moment. You can see the red spot here. And you saw it was just like 10 clicks of the mouse or something. Let me show you some of the more scientific tools. I'll just open up one of these images again. Maybe this one here. So we give them measuring tools. So as I said, if you want to measure the orbits, you can just measure distances very easily. And it gives it here in arc minutes and arc seconds. If you want to measure brightnesses of things, that's photometry. So there's your aperture. Just measure the brightness of that moon. Slide over and measure the brightness of this moon. In magnitude, which is an astronomical system, also in flux. But as we get farther in the labs, we sometimes have to measure magnitudes for many images at once. So let me show you batch photometry. This would be let's do a variable star in a globular cluster. It's a star cluster that orbits above our galaxy. It's in a different directory. I think it's under here. Standard candles. So yeah, all these images here. I'll load them in. Takes a second while it reads the headers off of all the images. And takes a second while it brings them in. So again, we're a little pixel limited here, but I happen to know we provide finder charts, and you can make a movie out of them and also tell by the one that's flickering. This is the variable star. So I'll just click on it and say variable. And we'll use this one as a reference because I happen to know its brightness. And let's see, I want to use the coordinate system that's built into the images, and we just find the sources in all the images. And so if I go to any other image, it should have found those stars in those images. Yep. And now next, and it does photometry on those 2 stars in all the images, gives you the table there, so you don't have to go through image by image, which would bore the students. And let me just plot it up here. At first it looks like a mess, but let me show you what is hidden in here. And again, this would take a grad student about a day to do with IRAF. We'll select the variable star, the reference star. You've got to subtract the reference out. And this is a star that's varying on a rapid time scale, yet you only get snippets. Like every night you get a little bit of data. So what is the pattern? What is the period? And you do period folding. But first you need to know the period. So it has built-in Fourier transform. And the students don't, this is great for the more advanced students that are using it, but the more introductory ones, they don't really need to know what this is, other than it gives them the period that they're looking for. There, so the period's about 0.56 days, so let's go back to the light curve plot, and we're going to period fold. This is 6 days of data. When I say 0.56, I can tweak it a little bit. Yeah, there we go. So you can see it's fading, and then it brightens, and then it repeats. And if I know the reference, the brightness of the reference star is about 13, then I say, well, if I have something that's repeating on this time scale, it's a particular type of standard candle. I know its luminosity. I just measured its brightness, hence I can compute its distance, and hence the distance to that star cluster. And maybe I'll show one more cool thing. I'm doing good on time. So overlay. We have telescopes all over the world. And so we can do parallax. You can observe a nearby object, something in the solar system, from two hemispheres simultaneously. And the nearby object will appear to be in different positions. It's like if you take your finger, stick it in front of your face, and close one. You can try it if you want. Close one eye, you see where your finger is, and switch the other eye, your finger appears to have moved. So you can measure distance in this way. It's how our brain gets an idea of depth. So let me get rid, let's call up some images here. And we'll go back to my workspace. And here they are, one taken from Chile, one taken from Moorhead Observatory in Chapel Hill simultaneously. And it's loaded in the headers. And it's somewhere here. Here it is. Let me get rid of this. It got in the way. Okay. So what we have here are the two images overlaid. It knows the positions of everything. It's already rotated them and stretched them such that they're the same. Here's the image from Moorhead. Here's the image from Chile. Here it's kind of half and half. You can see all the stars are centered on each other except this. This is our nearby object. The centers don't match up. And it's the parallax effect. It's an asteroid in the main belt between Mars and Jupiter. And so what we can do, I'll go to Flickr here, and we'll use the measuring tool. Like if I state the center of this reference star, the center is aligned. But let me go to the center of this asteroid here. And one and the other, and so I can tell there's about 5 arc seconds between them, and hence you can calculate the distance to the asteroid. And the students check, and it's indeed in the asteroid belt. There's just a quick sampling of various things from the labs. There are many other things that we do as well. But now let me show you what WebAssign's put together. Here, there are 8 labs total. Lab 2 and Lab 8 are traditional. Lab 2 uses globes to learn about season. Lab 8 uses rubber bands to learn about Hubble's law. The rest are Skynet-based. The first one's basically teaching you how to use Skynet. I didn't want to go to the edit menu. I just want to view the lab. Slide it over here. So we have some introductory stuff at the top. Basically, this is the introductory week, so they get lots of introduction. But each week there's a lab summary by one of the TAs. We've been videotaping them. And so for the online students who don't have the benefit of that, they can watch online. Here, I'll just show you this one. Maybe I'll zoom ahead here. Around 4:30, I think I want to get to. So here we're showing our telescope on campus, which is also on Skynet. The students are learning how to submit jobs in the system, and they see a telescope moving before them. My postdoc clues. One of the students just put an observation into the system. This big telescope in front of them moves. Now the dome starts moving, and you can just see the smiles appearing on their faces. But you don't need to have a telescope locally to do it. Anyway, let's go back to the labs. So it starts off with links to videos, and then as we go down here, they've coded the questions. They've used this accordion structure, which is very convenient. The goals of the lab, this one's basically learning how to use the system. Equipment is just a computer. And then background about the site and the telescopes and gamma ray bursts and how telescopes work. And then maybe I'll just hop down to one of these, how to observe with Skynet. And so we have tutorial videos. screen captures from some of my TAs.
Skynet.unc.edu.
Basically what I showed you before, but we have lots of these built into the labs to make it kind of convenient for the students, especially for the online students. And let me just go to Lab 3, and I'll show you something else. This is the one where they figure out the mass of a planet by tracking an orbit. And so measure the orbit. Oh, this is where they input their measurements. But let me go down here where they actually determine the mass. They got to determine the mass, they have to figure out the orbit. Again, we have a tutorial, but we also have this graphing tool that they use for many of the different labs. And this is being served off the same server at UNC. And some of the labs require them to plot stuff without, we don't necessarily want to mess with Excel because we have 1,000 students a year, so we built this custom tool. Here's the one for orbit determination. And so let's see, this is just fake data in there at the moment, but you can play with the orbital parameters. On the y-axis, you have how far it is from the planet. The x-axis is time. You can figure out the period, the semi-major axis, which is how big the orbit is. And so they just do it by eye, then they can take their values and stick that back into their WebAssign calculations. So let's see, maybe, they're all customized. In one, we figure out whether the Earth's at the center of the universe or the sun, heliocentric, geocentric debate, and you get different phases for Venus. So using the measuring tool, they measure the phase of Venus, the angular size, and they plot it up here. There's some fake data in here at the moment, but this is what you expect in a heliocentric model. In a geocentric model, you never get a full Venus, and so they're able to distinguish what kind of universe we live in, at least from that historical debate. There's a scatter plot for a different lab where they're measuring our position in the galaxy, and dual. Anyway, let me just go back to the PowerPoint here, wrap up, if I can find it. Okay, so let me just, in the final few minutes here, put it into a kind of a broader context. I've shown you one laboratory course that we've developed and continue to improve upon, but it's part of 4 introductory astronomy courses that we're putting together. 2 are lecture courses. One's on the solar system, and that one's just about ready. In fact, we do use it in WebAssign, but in terms of making it available for others, for our online students, we currently have about 100 online students a year, but we're going to push. We think we can increase those numbers tremendously. Lots of interesting things going on in online education right now. Anyway, we have a solar system course, a stars, galaxies, and cosmology course would be next, and the 2 lab courses are place in space. I just showed you there's another one in the works called astrophotography, which is what the kids really want to do. They really want to make the pretty pictures. That eats up more time. The Our Place in Space course is designed to get as much bang for the buck, as much science out of as few exposures as possible, so it's not too taxing of the system. But this is all in development, and the goal between these 4 courses is to bring them out to the public who just want to take them for fun. They can watch the videos online. If they want to, they can do the WebAssigns. Or students, and I've already mentioned the online students who go through the Friday Center, but also on campus. And we've been doing them at Chapel Hill for a few years. Guilford College is going to, a small private college, is going to start doing them in spring. And we have NSF proposals with NCA&T and Wake Tech that if we're funded, we'll not only start doing these curricula there, but there'll be team teaching, and people from my group at UNC will come out and help with the training and the first-time teaching of these labs and the lecture courses. And we're putting all this stuff currently on a YouTube channel. We're going to build a kind of a main site describing the whole project, but first we're trying to build up the YouTube channel. Let me just show that to you real quick. It's not it. So Project Intro Astro. So if you go to YouTube and just search for Intro Astro, our channel will come up. And there's some descriptive information here, basically what I've just told you. And it's all organized by lesson. Here's the Astro 101 course in orientation. Lesson 1, which is a playlist of, I think, 9 different units. And then there are 9 lessons in Astro 101. Then we have the lab orientation. If you're interested in the laboratory course, this is a good place to go to get a preview, kind of an overview of what we do. Then there would be lab summaries, which are taught by the teaching assistants. And I just keep videotaping them over and over, different teaching assistants, until I get decent ones. And so I'll keep replacing these, and they'll get better and better. Most of these are me or my postdoc clues. And most of this should be built by end of summer or partway into fall. Most of these videos should be there. And let me start this back up, and maybe it is started. And so you're saying, okay, I can't put a telescope on Skynet. That's too big of a project for me. As I said, we're always looking for ways to open access. We have plans down the road to open it on kind of a competitive market pay-as-you-go between all the Skynet telescopes to drive down costs. This is in the works with NSF. But until then, that will open up to everybody. But until then, we're looking for different ways. And one way that we've decided to target, because we can write NSF proposals. Again, my group costs $250,000 a year to run. I'm always looking for things that might please NSF. This is one of them. So this laboratory course that I've just showed you, we're opening up to any institution that wants to take it on. And you'll get access to Skynet and the prompt telescopes in Chile, priority access to the telescopes in Chile, enough to do the labs for your students if you're so inclined to try the course. And I think I'll stop there. So thank you.
Does anyone have any questions for Dan about anything he's shown today? Yes.
So let's say that you're a high school astronomy teacher in Ohio that wants to hook into something like this. Right now, to do that, you have to have a telescope that can be put on the net to work this, or? So the best strategy for you right now in terms of what we have available, there are a number of different options. One, if you're interested in the labs that we've built, if you go and use that curriculum, then you're going to have the access. We can include you on our NSF proposals. That's what we get out of it. It looks good. We're broadening access to people all across the place. There's also a program on the, if you go to the Skynet main page, you can apply for time. We have a wealthy donor, Robert Ayers, who has bought a certain amount of time, and you can write a little proposal and gain time for specific projects, even if they're education. Mostly it's professional stuff that's been funded, but he is open to funding educational efforts as well. You could do a lot with a little bit of time. The third way is you can purchase the time through a donation to UNC, and the time goes for like $50 an hour. And I'm not saying that to sell it to you, because I've given you this other way in that doesn't cost the institution any money. But we do sell a lot of our time to scientists. It helps us pay the bills.
So with WebAssign, did you work with the custom editing team and do all the parts of things that you have put as a WebAssign? Yes,
yes. I worked very closely with them, Karen in particular. I don't know. There we go. And she's been great in putting this together. And it's been a good process, because it's a pretty complicated thing to develop. I provided Word documents and PDFs that the students had been using before, and they're just clumsy and clunky. And now the thing is so nice. They have the lab. It asks them the question. There's the place to give the answer right there in the lab as they go through it. There are places for essays. And it's been working great. As I said, we do about 1,000 students a year on this curriculum now, and it's going to increase now that other schools are taking a look at it as well. And of course, as we go through, we learn new things. Oh, I should rephrase this question, or I need to change this. And so we have a Google spreadsheet where I keep putting revisions, and they jump in periodically and implement them.
I just saw your questions there with all the little plus signs and boxes that pop out the separate sections. That was all like one massive question with all that stuff in there. Was that just special HTML, or is that something special in WebAssign?
That's what WebAssign has put together. I don't know that.
Yeah, that's a new style of formatting we're using for particularly long questions, and we internally call it like an accordion style, so that students can focus on individual parts and then collapse what's not there. So we've been using it a lot for things like Dan's labs as well as other labs. We do it a lot now with longer tutorials. So you'll see a lot more of that in WebAssign as product is going forward, like as new stuff comes out. We'll be using it to make it much simpler for students to focus. Yeah, you could write your own questions. I don't know how it's documented in the question coding, but that's a great question to ask at the advanced question coding breakout this afternoon.
Most of our labs we were able to get into one question, which is particularly nice. The longer ones, 2 questions.
In your example of Guilford, when you export to a small institution like that, are they basically getting access to everything that your students have access to? They're getting, I mean, they'll be using the YouTube channel, they'll be using the WebAssign component, and also getting telescope time?
Yes.
That's
Yep,
wonderful.
whole package. Now, in the case of Guilford, they're just adopting the laboratory course. And so, yeah, on the YouTube channel, there are the lab summaries by my TAs. But they're going to have their own, they're going to have a professor in their lab. So he's going to be better to listen to than my TAs, most likely. But the other institutions I listed, if we get funded by NSF, will also be implementing lecture curricula. And we'll make more use of the videos there. I've been funded to, and this scares the hell out of me because the course has been so successful, but to completely transition to flipping the classroom and active learning. So the students will actually, at UNC anyway, be watching the videos ahead of time, not this fall, but next fall. And then the whole class time is all going to be active, interactive, and e-polling type stuff. Hopefully it doesn't scare people away.
Excellent. Well, thank you so much, Dan. We
Thank
really
you.
appreciate
My
it.
pleasure.